All right, here's to escaping 21st grade. So, thank you all so much for being here today, both in person and on Zoom. I'm excited to share my dissertation with you guys titled Scalable Probabilistic Modeling and Inference with Structured Latent Representations. But first, we're going to take a quick peek through my camera roll. I found an obscene amount of pictures of these F4 Phantom jets. It's my favorite jet. I have actually well over 100 pictures. This is an aggressive down selection. I also take a lot of pictures of jets while I'm waiting at the airport at my gate, although I think I took the picture of that Dreamliner from the bathroom at the Denver airport. Here's me daydreaming about being a part of the Top Gun mission, technically an airplane picture. And then here is an RC plane that I built about 10 seconds after it's made in flight. And this is why you should always validate your work in simulation first. And so if we take a probabilistic lens of these pictures, we view these as samples drawn from the space of all possible aircraft images, governed by some probability distribution. And the goal of probabilistic modeling is to learn some model parameterized by theta, oftentimes, though not always, a neural network, which learns some distribution which is close to that distribution over ground truth samples. And in practice, this model learns and represents some mapping between a really simple latent distribution and that more complicated learned distribution. Now, the word latent has some strong connections to latent variable modeling with connotations of dimensionality reduction. For this presentation, we're going to adopt a unified perspective, which says that a latent distribution is the source distribution, which generates these unobserved samples, which are passed through the model. And we like working with latent distributions because they tend to have some really nice properties. They tend to be more interpretable than the complex data density. Oftentimes, though not always, they're lower dimensional, so it gives us a lower dimensional space to do our tasks in. And they also have some nice known statistical properties, such as a known mean or covariance. And so in the title, we talked about probabilistic modeling and inference. So to just break that down a little bit, probabilistic modeling comes with two main subroutines that we care about. The first one is density estimation, and that's related to how likely or unlikely data samples are. So the idea here is if we learn some representative distribution over the space of airplane pictures, if you give me a picture of a strawberry, it should flag as really unlikely in that learned distribution. The other subroutine that we care about, and the one that probably folks are most familiar with, is generative sampling. And this is where you draw some sample from that simple latent distribution and you push it forwards through your learned model. And the idea is that the generated sample should plausibly look as if it could have come from the true data distribution. So here we see there's a fairly close match. So we've been talking about this example of distributions over airplane pictures, but there's all sorts of variables that we might want to learn distributions over. One such set of variables would be aircraft trajectories. So here we have a graphic showing an aircraft ground collision avoidance system, or GCAS. And the idea is if we have a diving airplane, we want this system to recover the aircraft by rolling its wings level and then pulling up to hopefully avoid a collision with the ground. And if we simulate a bunch of these rollouts and put the system to the test, we see that there starts to be a distribution or patterns that emerge in this data over aircraft trajectories. And we might want to learn about these distributions so we can reason about things such as safety or failure modes. The other task we'll talk about in this talk is inference, which involves estimating posterior distributions given some learned model and some conditioning variable. So here I have some region which might govern, say, a distribution over all the pictures of my RC plane failures. And the idea is if we were to integrate over this region, it would give us some idea of what's the probability of having this picture of an RC plane failure. And to put that in the context of this GCAS problem, right? So if we have this ground collision avoidance system recovering aircraft, we have a couple different failure modes we might be interested in. We might be interested in cases where the aircraft collides with the ground, or if we pull up too steeply and the aircraft enters an aerodynamic stall. And so we'll want to perform some inference tasks to reason about how likely these outcomes are. And in practice, inference requires integrating over intractable integrals, so we'll typically resort to sample-based methods to approximate these integrals. And to frame these contributions in the broader context of modern AI research, many folks these days focus on different model architectures, diffusion models or GANs, different ways of representing this function f. Some folks focus on training schemes, where we take data from the real world and figure out how to train our model on that data. Some folks do applications, such as style transfer. If you have a model which has learned some distribution over aircraft pictures, how can you then transfer that knowledge to some other downstream application? In this work, we're predominantly focused on this latent distribution, and in particular, how we can structure this latent distribution in a way to scale up these modeling and inference tasks. In particular, we're looking for ways to place inductive biases on these latent distributions. And by inductive bias, I mean a set of assumptions that our learning algorithm makes to generalize beyond its training data. In other words, it's how we help our model make an educated guess about data that it hasn't seen before. And while we're wrapping up with some definitions here, I'll be talking about scalable algorithms throughout this dissertation. And by scalable, we can either mean working in higher dimensions, such as bigger and bigger images, longer horizons, if we're talking about a robotic trajectory, or less training effort. For example, learning a model gets the same performance, but with less training time. So the overall dissertation contribution here is we scale probabilistic modeling and inference algorithms by using inductive biases that exploit latent structure in these latent distributions. And to that end, we put forth 3 different contributions we'll be talking about today. The first is called latent space importance sampling. And so the idea is we have this inference task where we want to estimate how much probability mass lives in this red region. And what we do is we actually map these regions backwards through an invertible model, and we solve the task in a latent space which is more isotropic in nature and where it's easier to solve this task. For our second contribution, we revisit this inference task. It's called importance sampling. And as part of this method, it's generally desirable to draw samples that fall inside this red failure region. And to do that, we want to learn some distribution which closely aligns with this red region. Now, learning such a distribution can be pretty challenging in high dimensions. So we learn a low rank distribution, which has some mapping from a low dimensional latent space up to the higher dimensional space that we actually care about. And then lastly, we combine some of these mechanisms that we've talked about previously. We take the exact same low rank distribution that we previously introduced. And so it has a low dimensional latent space, a higher dimensional data space. And this entire distribution, in turn, becomes the latent distribution for a more expressive flow model. And we're able to obtain better generative performance with this method. And first, there's going to be some ASMR on this mic of me drinking tea. Before diving into these contributions, I want to quickly try to level set us as best we can by going through a couple of the core ideas that will appear throughout this work. The first idea I want to talk about is a type of model called a normalizing flow. And so flows represent modern state-of-the-art as far as probabilistic modeling goes. And the way it works, I think, is a super neat mathematical idea. When you draw samples from these flows, you start with a simple latent distribution, and you push them through a series of transformations. You take these samples and you stretch them, you rotate them until they more closely resemble the distribution that you're trying to learn. Now, if we enforce certain mathematical properties of these transformations, namely if we make sure that they're invertible and differentiable, we can actually go backwards through this transformation. We can effectively undo all the changes that we've made to this data, and we can end up back in our simple latent space where we can perform density estimation. Now, early flows were created by stacking different bijective functions together, but more recently, folks realized that we can actually make this a continuous time transformation. So instead of stacking different functions together, we can actually use a neural ordinary differential equation, which learns a smooth mapping from our simple latent distribution, shown on the left, to the data distribution that we care about on the right. Now, flows are modern state-of-the-art for probabilistic modeling, but 25 years ago, we didn't have flows. Instead, we had this latent variable model called probabilistic principal component analyzer. And I think some of the most fun I've had at this work is finding sort of like a new home, a new context for this really classical latent variable model. And so on screen here, I've shown what we would call like the generative story for this particular model. The idea here is that we want to learn some high dimensional distribution, but we're actually going to start in a lower dimensional space. We're going to draw a sample from this purple latent distribution shown on the left, and we're going to project it up to a higher dimensional space by projecting it onto one of the learned principal components of the data. And if we layer on this isotropic noise model, then we end up with contour lines for a distribution which are Gaussian in nature. And so this is how we can come up with a low rank approximation to a Gaussian distribution. And so this is kind of a simple example here shown going from 1 to 2D, but we can actually use these models to learn really expressive high dimensional distributions. So to sort of walk through this example quickly, here we have a data set of images of faces, and we can sort of average a bunch of these images together to come up with an average face or a mean face shown here. This ghostly sort of true crime looking photo here is the learned principal component. And then I think there's a super neat interpretation we have here, which is by stepping along this principal component, we can sort of add or subtract the effects. And so in this case we can actually see it's a sunglasses principal component. And so if we step in one direction, we sort of layer sunglasses onto this face, and if we step in the other direction, we remove the sunglasses. So I think these principal components tend to come with some really nice physical interpretations. And the last topic I want to introduce today is probably going to be one of the most complicated. So I'll do my best to introduce it quickly via analogy here. It's this topic called importance sampling. And at a really high level, importance sampling is an efficient way of estimating the probability of failure for a system. So if we have some robotic simulator, we want to come up with an estimate of how likely that system is to fail. And so sort of the analogous way of explaining it here would be like, say we have this dartboard, and I want to estimate how much area lives inside the bullseye of this dartboard. I don't get a ruler, but I do get a big bucket of darts that I can throw at this board. And so sort of the empirical way of estimating this area ratio is to just start throwing darts at the board. And my throws are more or less uniform random. And so as we throw 100, 500, or 1,000 darts at the board, right, eventually we'll start to cover the board. And in the limit, as we completely fill this board with darts, the percentage of darts that fall inside that bullseye will tell you the area ratio of the bullseye to the entire dartboard. Now, this is it's fairly sample inefficient, especially if I'm throwing the darts, right? Obviously, not many darts will fall inside the bullseye. And so the big idea of importance sampling here is, what if we were able to somehow bias our search towards the region of interest? So the idea is, what if we were able to take this region, blow it up to full size, so now our bullseye is proportionally a much bigger percentage of the space. And so now if we throw darts at the bullseye, even just 100 darts, we start to land more darts on the target. Now, of course, this doesn't quite give us the ratio that we were originally after, because we biased our search towards this bullseye. And so I use this example to really highlight the two steps of importance sampling, which is, first, we got to focus our search, but then two, you have to reweight your samples because they're now coming from some biased region of your search space. In the context of robotics, we might have some underlying distribution with a known failure region, shown by this red ellipse right here. And if we just drew samples from some sort of diffuse prior, very few samples would fall in that failure region. So what we can do is we can learn what's called a proposal distribution, which is more closely aligned with our failure region. And then when we draw samples, more of them will fall inside the proverbial bullseye, the failure region here. But since we're coming from a biased distribution, we have to remember to reweight the samples, and we reweight them with something called the importance ratio. So it's okay if not all of this sticks. I really want the main takeaway here to be, importance sampling is a technique for estimating the probability of failure of a system and estimating it efficiently. And the way we do it is by first focusing our search, and then we have to reweight the samples to account for the bias in our search. And with that, I think we're about ready to jump into the first contribution here, which is called latent space importance sampling. And so again, the idea here is we're going to be doing this importance sampling task, but instead of performing it in the data space, we're actually going to map our regions backwards through an invertible normalizing flow, and we're going to solve this task in the more regularized isotropic latent space of that flow model. And I want to start by revisiting this graphic that we just talked about. And this is something that I noticed a couple years ago when I first started doing some importance sampling for the first time. So we have samples from our simulator. We have this failure region. And in sort of vanilla importance sampling, we would learn some proposal, which we try to fit to this failure region. And then we can draw samples from that proposal. But if you notice this distribution on the left, we sort of have two failure modes here for this particular system. And our proposal only found one of them. So when we draw samples from that proposal, not only are we sort of missing this failure mode, which lives right here, but we also have placed lots of samples in this region of vanishingly low density between the two arms of this data set. And so that sort of started as the nexus for this idea, which is, what if we were able to learn an invertible transformation, which goes from this more complicated data space to a latent space, which is more isotropic in nature, where regions of similar likelihood are placed by each other, and where different failure modes tend to get smushed closer together. And what we found sort of empirically at first was that if we then fit a proposal distribution in this latent space and then map those samples back to our data space, we end up with samples that recover our failure modes with more fidelity, and they also have greater respect for the actual underlying distribution. So we're not putting so many samples in this region of low likelihood right here. And so the main hypothesis for this work is that mode dropping will be reduced when importance sampling occurs in the latent space of a normalizing flow. Flows themselves have been used as proposal distributions before, but this tends to require a complex training procedure where you sort of interleave the flow training process along with the importance sampling steps. A couple researchers have done Monte Carlo methods in the latent space of flow models before, but their main goal has been to limit out-of-distribution samples, whereas our goal is to take an AI safety validation lens and use the latent space for importance sampling. We also have some connections to conditional flow sampling, where the big idea is that you want to learn mappings between certain regions of latent space to particular regions in your data space. And to formalize the inputs and outputs of this method, so this algorithm takes as input a data simulator, a pre-trained normalizing flow, and a set of failure instances. And the output is going to be a learned latent proposal distribution with some estimate of the probability of failure for that system. And the end goal of this approach is to reduce mode dropping compared to more vanilla importance sampling. And so to start here, I have a synthetic data set with a collection of known failure points. These can either come from the held out data set used to train your flow, if you have them, or they can also be user defined and correspond to some sort of known safety threshold, right? Maybe these correspond to like servo motor limits or actuator limits for your system, right? So they define some sort of nice unsafe region here. And so what we do with this method is we map this learned distribution through our pre-trained normalizing flow to a latent space which more closely resembles a standard normal distribution. The idea here is that it's more isotropic in nature, and we sort of have taken this bimodal distribution and compressed it into a unimodal distribution. Now we had some really nicely defined failure regions out in data space, and now they've kind of been smushed and changed a little bit and sort of mushed together. And so we need to find some compact way of representing these failure regions. And one of the key contributions for this work is that we choose to represent these regions with the minimum volume covering ellipsoid, which covers those two sets of points which came from those two failure regions. And this is a really attractive formulation for a couple of reasons. First off, finding the min volume covering ellipsoid is a convex optimization problem, which means that we can compute it pretty cheaply and computationally efficiently, even for really high dimensions. The other really nice property is that for importance sampling, we need some sort of cost function to drive our search for a proposal distribution towards our known failure regions. And computing distance between an arbitrary shape is a really challenging task, but it's actually very cheap to compute the distance from some point to an ellipsoid, even in really high dimensions. And so we use the distance to these sets as the cost function, which drives our search for a proposal towards these failure regions. Then when we take samples from these points and map them back to our data space, we see that almost all the points we generate are failures, and we have very few wasted samples which are non-failures. And so just to compare samples from our proposal shown on the left with ground truth data shown on the right, we notice the ground truth data exhibits a sort of long tail behavior for the failures. And the samples from our latent space proposal closely match the shape of these data samples without having all these non-failure samples. And so to compare, here's samples from a proposal which we learned in data space. As we can see, it's certainly nowhere near as good of a match as the learned data. We actually had a little bit of a mode collapse here, I think, and we have these two distributions trying to cover both modes at the same time. And just to confirm, just to clarify, these are using the same random seeds. The only thing that changed from left and the right is where we conducted the importance sampling. And a couple different random seeds. Again, the data space importance sampling performs a little bit better here, but we still generate a lot of low likelihood samples. And for our experiment suite here, we first estimate the probability of collision for a diving F-16, as well as the probability of oversteer for a cornering race car. And so for this F-16 task, we measure success or failure based on the end state of the aircraft. So we largely ignore the trajectory, and instead we consider failure if it collides with the ground or if it enters an aerodynamic stall. And we record a number of metrics to validate this approach. The two that I want to highlight today are log likelihood and mode coverage. So here I show some log likelihood results for the cornering race car on the left, the F-16 GCAS on the right. Our methods are both shown on the left here. We do latent space importance sampling with both the cross-entropy importance sampling method as well as sequential importance sampling. And in both cases, we obtain a lower negative log likelihood value, which means that the samples that we generate are a closer match to the true failures from the system. And also at the top of this talk, right, we talked about how the main goal here is to reduce this issue of mode dropping. And so to that end, we report this coverage metric, which came out from an ICML in 2020. The big idea here is that you want to record the ratio of fake ground truth samples, which contain at least one of your fake samples in the neighborhood. And so we obtain higher coverage scores, which means that we're largely able to reduce this issue of mode dropping, especially for this F-16 ground collision task, where we see that performing importance sampling in data space actually suffers this mode collapse issue where it largely misses all the modes altogether. And the key takeaway from this work is that fitting importance sampling proposals is easier if you do that in an isotropic latent space. The second contribution that I'd like to highlight today sort of builds on this idea of importance sampling, and we introduce these low-rank mixture proposals. So the idea here is we want to learn a really high-dimensional proposal distribution, but we do so by learning a model which has a low-dimensional latent space. And so I think this is the last time I revisit this graphic. One thing that I sort of glossed over in the previous time through is that we've been talking so far about these parametric proposal distributions. And what I mean by that is these proposals come from some parameterized family of distributions, in this case a multivariate Gaussian distribution. And this has some really nice properties. It means that we can generally estimate these parameters quickly for adaptive importance sampling methods using expectation maximization, for example. The drawback of using a parametric family of distributions is that you have to estimate a covariance matrix. And so to sort of illustrate why this is a difficult thing to do in high dimensions, I performed this quick little experiment where I draw 200 samples in dimensions ranging from 10 up to 200. I fit an empirical covariance matrix on this data, and then I report the condition number of that covariance matrix. And the condition number is related to the invertibility of your matrix. As it grows off to infinity, it becomes impossible to invert that matrix. And in the limit, as the number of samples that you have to fit that data approaches the actual dimensionality of your problem, your matrix becomes invertible, or non-invertible, sorry. All this to say that fitting these empirical covariance matrices is really hard for high-dimensional tasks. Fortunately, we have this model that we can use which learns low-rank approximations to these covariance matrices, and that's this mixture of probabilistic PCA. So this Gaussian distribution shown in green on the right would typically be governed by some full-rank covariance matrix. But here we have this mapping, which goes from a low-dimensional latent space up to that high-dimensional space. We've effectively learned a low-rank approximation to this covariance matrix. MPPCA also has this really nice characteristic, which is that we have closed form updates for its parameters, which means that we can cheaply update these parameters on the fly for adaptive importance sampling algorithms using expectation maximization, for example. So we can effectively automatically determine some set of means and some principal components, and then a learned noise model, which ultimately gives us some learned log likelihood over this data. And using expectation maximization, we're actually guaranteed to get a local maximum for this data. An alternate approach to using MPPCA for learning a low-rank covariance matrix is mixtures of factor analyzers. But these don't admit batched closed-form parameter updates because they don't assume an isotropic noise model. We could also turn to non-parametric importance sampling methods, where instead of using parameterized family distributions, we represent failure distributions with samples. But then again, we still lose this closed-form updates, which is what lets us do adaptive importance sampling quickly. So if we want to do closed-form updates, we'll have to resort to some sort of parametric importance sampling. But again, this forces us to estimate these really high-dimensional covariance matrices where they can become ill-conditioned. So to formalize our proposed approach here, this problem takes as input a data simulator, as well as a problem-specific cost function to guide our search towards these failure regions. It outputs a learned MPPCA proposal distribution, as well as an estimate of the probability of failure, with the end goal being here, let's scale importance sampling to a higher dimensional system. And so whereas before we defined failure based on simply the end state of the aircraft, now we're going to a higher dimensional problem, which is actually looking at the entire trajectory of the aircraft. So now there's a temporal component in here as well. And so while we measure failure based on the trajectory of the aircraft, whether or not the aircraft stalls or crashes, we're actually learning proposal distributions on sensor disturbances. The idea here being if we can figure out how to corrupt one of these sensors, we can induce a crash for the aircraft. For example, the GCAS system uses a roll sensor to figure out how to roll the aircraft before pulling up. If you can add noise to that roll sensor, then it might never roll the aircraft in time to recover it. And so here's some plots from some of our experimental results. And so we have some simulated data from our actual simulator shown in this big plot on the left. It looks a little different than the plots before. Here we're showing angle of attack on the horizontal axis and altitude on the vertical axis. And so the idea here being that your system fails if you collide with the ground, which is when you enter this region right here, or if you enter an aerodynamic stall, which is when you enter this region right here. And so our low-rank proposal distributions are shown for both cross-entropy and sequential importance sampling here on the top row. And these methods are able to find failures which appear in both regions. We also have samples which more closely resemble the ground truth distribution, both quantitatively and qualitatively. We benchmark against a couple methods that use full-rank covariance matrices, shown on the bottom here. And we can see that they actually both experience a mode collapse, in particular cross-entropy with a full-rank Gaussian mixture model, where it completely missed failures which fall into this ground collision region, which is kind of a big miss if you're trying to validate a ground collision avoidance system. We also validate on a Duffing oscillator, where failures are defined if you enter one of these regions of maximal displacement. And so on the top, we have our two methods, which again, both quantitatively and qualitatively find distributions which are a close match to this ground truth, versus the full rank methods, which start to suffer a bit of a mode collapse here, where we put a lot of samples in one failure mode but not the other. And sequential importance sampling with the full rank mixture also starts to generate a lot of low likelihood samples as well. And then finally, we test with the so-called branches problem, which is actually 40 dimensions, shown here visualized in 2. And the idea here is you want to put failures that fall outside of this box. Our low-rank methods are able to scale up to this high-dimensional task and put failures in all 4 modes, versus importance sampling with a full-rank covariance matrix, where not only have we had a bit of a mode collapse, mode dropping, where we drop this failure mode right here, but we also have this really degenerate component right here. And so the main takeaway from this work is that high-dimensional proposals are effectively represented by these low-rank mixture models. And then finally, the last contribution I want to talk about today, the one that I think I'm most excited about, which is learning expressive flow base distributions. And so the idea here is we're going to recycle this MPPCA model that we just introduced in the previous chapter. So we're going to have this low rank, this distribution with low rank covariance estimates. And this entire distribution is going to become the latent distribution for a much bigger normalizing flow model. And so I want to revisit this continuous normalizing flow that we talked about earlier in the talk. Again, we have this continuous transformation, which takes samples from our simple latent distribution shown on the left, and it maps it over to this data density on the right. And I've pulled these distributions apart so that we can sort of see this transformation, but it's actually a little bit misleading. We don't really have this extra displacement. It actually sort of all happens in place, right? And so this is actually what that learned transformation looks like. And what you notice here is that these trajectories these particles follow are actually, they can be very curved in nature, which isn't just like a theoretical exercise here, because for these continuous normalizing flows, we use numerical solvers to integrate through the learned trajectory map to take us from this latent distribution to this data distribution. And so if your dynamics here are sort of ill-conditioned or ill-posed, your adaptive step ODE solver will have a tough time integrating through this vector field. You'll also have reconstruction error if you're using like a fixed step ODE solver here. And so in general, we want to learn some method to simplify this learned flow transformation. And so here's sort of the thought process that went through my head. This idea came to me at a coffee shop, which I think felt a lot more scholarly than the shower, which is where most of my other ideas come from, I think. So we have what we call vanilla flow matching here, right? So flow matching is how we train these continuous normalizing flows. And if we don't place any inductive bias on the training process, we can get trajectories which are all over the place, arbitrarily good, bad, they might be highly curved. Recently, researchers have investigated how to connect ideas from optimal transport to training these models, with the idea being we can straighten out these trajectories, which makes them easier to integrate. The idea I had was, what if we had a learned prior, which was already a really close match to your data in the first place? Then there's actually very little pushing your model has to do to push samples from the base distribution to the data density. In the limit, as you actually if your prior was the data distribution, you wouldn't have to push the samples at all. In this case, right, we have a very close match at the top of the distribution, so there's not, we don't have to integrate through a vector field too much up there. We just have to push around some samples at the bottom of this distribution. So the main hypothesis for this work being flow transformations will be simplified if we learn a latent distribution which closely matches our data distribution. Now this sounds almost too simple to work in practice, and I think that the real challenge here is that it comes with a set of really stringent assumptions about this learned prior. We would need a prior for this to work which is highly expressive in of its own right. If it's not expressive enough, then we might as well just use a standard normal distribution as your prior, which most flows use anyway. It also needs to be really parameter efficient and have minimal training overhead, right? If you're going to spend all this time training your prior distribution, you might as well just use it to train your flow model in the first place. Fortunately, we have such a model which checks all these boxes, and it's one of these probabilistic principal component analyzers that we've introduced in this talk. Just to clarify, these pictures here are generated from a low-rank Gaussian mixture model. This is not a fancy neural network which learns these images. This is a low-rank mixture model. And so here we have different component means on the top with some of the learned principal components. And so we can see how one of these really simple models can learn a complex distribution over all sorts of different phase shapes and styles here. So the real workhorse for this idea is going to be this mixture as a probabilistic PCA. One of the main advantages is that they can be fit really quickly and cheaply using expectation maximization. We're among the first researchers to think about fitting these latent GMMs. A couple other researchers have used really simple GMMs to improve classification in the latent space of flows. And in spirit, this idea has some close connections to training with optimal transport, where the end goal is to simplify your learned flow transformation. Optimal transport uses OT to straighten the paths to simplify the transformation. We're trying to shorten the paths by basically learning a model which is already close to the data density. And so as input, this approach takes in a training data set, an MPPCA distribution, and an untrained flow model. And it will output a trained flow model where we have an MPPCA latent distribution, with the end goal being, let's simplify this learned flow transformation. And here's actually what this looks like in practice. So at the top, we have samples from our flow with an MPPCA latent distribution. And on the bottom, we have samples from a flow with a standard normal latent distribution, which is a common alternative. And so here's how to sort of interpret these image pairs. I've paired up images from 3 different image data sets here. The image on the left for each pair is what we generate after 1 training epoch. And the image on the right is what we generated after 100 training epochs. In other words, the image on the left is what we get after roughly 1 minute of training, and the image on the right is what we get after about an hour of training. And the big takeaway here being, right, by having a learned MPPCA base, we're effectively warm-started the flow training procedure. So it spends more of its time sort of refining the transformation as opposed to learning this structure in the first place. So we perform, sort of validate this approach, we perform a density estimation task for which we record log likelihood values. We perform an image generation task for which we report the NDB score, which is a measure of how good your generated images are. And then lastly, we report function evaluations, which is going to be our metric for whether or not we've simplified the flow transformation, because an adaptive step ODE solver should take fewer function calls if you've learned a simple transformation. And so here's some results on a tabular data set with negative log likelihood. Low score is better. Our method's on the left. And by achieving this lower score, the implication is that we've learned a model which is more accurately represents the ground truth distribution. We also report function evaluations. And we can see here, especially for this BSDS 300 data set shown on the right, we're actually able to cut the number of required function evaluations almost in half, meaning that we've learned this simple flow transformation. We generate images and record this NDB score, which is a measure of generation quality. Golf rules, low score is good, means that we're generating images which are a closer match to the ground truth density. And we're able to achieve NDB scores which are much lower than flows that have the standard normal base distribution. And finally, we report the function evals. And again, we're able to cut the number of required function evals almost in half, again, sort of validating the fact that we've been able to simplify this learned flow transformation. And as an added bonus, let's briefly talk about the overhead introduced by learning these flows. Again, it doesn't make a lot of sense to learn a strong prior if you could just spend that training time training your flow model in the first place. But for the image data sets where we train out to 100 epochs, the time required to fit the MPPCA model is just about 1 or 2% of the total training time. And there's also a nice perk for these tabular data sets. We train with early stopping, where we stop the training procedure if we're no longer improving the model. And early stopping actually triggers a lot earlier if we spend a little bit of upfront cost to sort of learn this strong base distribution. So you recover all your time spent fitting that model and then some. So to summarize the contributions from today, we talked about 3 different contributions to scale probabilistic modeling and inference algorithms. The first is latent space importance sampling, where we perform this importance sampling task in the latent space of a pre-trained normalizing flow, where the distribution is more isotropic and easier to explore. We next scaled up importance sampling to really high dimensions by learning these low-rank mixture models, these mixture proposals, where we have this mapping from a low-dimensional distribution up to the data density. And then finally, we took these low-rank distributions and we used them as the latent distribution for a bigger flow model to improve our generative performance. And I think these contributions open up a couple really interesting avenues of future work. For the latent importance sampling, I think the logical next step is to explore alternate failure region representations. The nice thing about these min-volume enclosing ellipsoids is that it's a convex problem, so it can be computed really cheaply. But in really high dimensions, an ellipsoid contains a lot of empty space. And so I think we'll want to figure out ways to sort of tighten these regions, perhaps using some flavor of partitioning. For the MPPCA high-dimensional proposal distributions, I think the next work will involve connecting the principal components of our learned model with the principal failure modes of the system. There was a really exciting moment during this publication where we looked at the first principal component of our learned model and saw that it very clearly corresponded to an early noise input on the roll sensor. I think there's lots of really strong intuitive connections between these learned principal components and the sorts of failures that will actually cause your system to fail. And so I think we can take sort of these lessons learned and apply them to all sorts of robotic systems. And then finally, for this flow MPPCA idea, I think it's really worthwhile to investigate the ramifications of having a mode collapse as you fit your MPPCA model. We didn't encounter this in practice because I think these models are really parameter efficient and expressive. But the key idea here is that we learn a strong prior. And I think we should evaluate what happens if you learn a really strong bad prior, right? And I think we could sort of artificially test this by holding out some of our training data to fit our MPPCA model, and then see what sort of effort the flow has to do to map from that base distribution out to the data distribution.